Good morning, children. Today we are going to learn about cells. What will happen when the cells are combined in a parallelly and serially? So we are going to describe or learn about the combination of cells and how they can be combined together and what will be the equivalent resistance and EMF of the cells when they are connected or combined serially and parallelly. So as I said from the name itself, there are two ways by which we can combine the cells together. A number of cells can be combined series and a number of cells can combine parallelly, and what will happen to its EMF and their internal resistance when they are combined in those two ways. Let's see. First, the serial combination of cells. See, a number of cells are combined serially. And for convenience, we take that all the individual EMF of the cells are same, or all these cells are identical. And here, for convenience, we are drawing only 3 cells, but assume that n cells are connected to each other. Okay, so the EMF of this first cell is E, and the second cell also E, and third cell also E. Okay, they are identical cells. They are connected serially, and an external resistance R is connected to this combination of these cells. Then an electric current I will flow through this circuit. So as we said, the cells are identical, so the EMF of the cells are same. So in order to find out the total EMF of this combination, okay, how we can find out the total combination? The EMF of the first cell plus EMF of the second cell, EMF of the third cell, EMF of the fourth cell, and so on, and the total EMF you can write as, what will be the total EMF? The EMF of one cell into the number of cells. So we say that N into E will be the total EMF of the cell. Then what will happen to the internal resistance? As each of these cells has an internal resistance R, then what will be the total internal resistance of the cell? The total internal resistance, as I said, if all these cells are identical, the internal resistance of each cells will be the same. So the R is the internal resistance of a single cell. Then the total internal resistance will be the sum of the internal resistance of all the cells connected to the circuit. That means n number of cells are connected, so the total internal resistance will be N into R. Then, and also another external resistor R is connected to the circuit. If the external resistor R is connected to the resistance, then what will be the total resistance of this circuit? Then the total resistance will be the total internal resistance of the cell, resistance of all the cells connected to the circuit plus the external resistance. That means we can get as N into R plus capital R. So N R plus R. Now, if we have the value of the total EMF and total resistance of the circuit, and now the current flowing through the circuit can be, so current I is equal to, as I said, from the equation that we derived in the previous session, current I is equal to the total EMF of the cell divided by the total resistance of the cell. So we say that What is the total EMF? That is N into E is the total EMF of the cell, and the total resistance of the circuit is N into R plus the capital letter R. So that is the total resistance of the circuit. And now here there are two conditions. In order to, when we have the maximum current flowing through this circuit. So in order to find out the maximum current flowing through the circuit, we need to consider two conditions. And the first condition is when the external resistance R connected to the circuit is less than the internal resistance of the cell. So what is the external resistance? If R is less than, much less than the total internal resistance N into R, then what will be the current? Then we will get a value for the current. See, if the R is much smaller than the internal resistance of all the cells, then and this time R can be negligible. Okay, it can be negligible. So what will N and N will be cancelled there. Then I is equal to, and this time will be negligible. Then what will be the equation? E by R will be the value for current. I is equal to E by R. And the second condition is what if the value of external resistance is greater than the internal resistance, the total internal resistance of the circuit, then this term can be negligible. Okay, so then we will get I is equal to N into E divided by R. Okay, so in which condition we will have the maximum value for the current? So here the second equation, if you see, if R is much greater than the total internal resistance of the circuit, then the value of current will be maximum in this case. Okay, when the cells are, a number of cells are connected serially, the maximum current will be flowing through the circuit when the external resistance is much greater than the total internal resistance of the cells or total internal resistance of the circuit. And next let us see what happens to the total EMF of the cells and the internal resistance of the cell when they are connected parallelly. And here the diagram, you can see that a number of resistors are connected parallel to each other, and you know that only three cells are here, but assume that n number of cells are connected to the circuit. Then what will be the total EMF of the cell? The total EMF of the cell will be, as I said already, these cells are identical, so the EMF of all these cells are same. To find out the equivalent resistance of this is, so 1 by R equivalent, so the resistance that is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus etc. And how many? 1 by Rn. Since n number of cells are connected there, and this will be the equivalent resistance of the cells when they are connected parallelly. If n number of cells are connected parallelly, then the equivalent resistance 1 by R equivalent is equal to, and the same case now we can find out the total EMF. What will be the total EMF? Since all these cells are identical cells, all they have the same EMF. So the total EMF will be, since all these cells are connected in parallelly, and the total EMF will be equal to the EMF of a single cell, that is E. And then what will be total internal resistance? Total internal resistance will be equal to, R divided by N will be the total internal resistance. If the total internal resistance of the cells are R divided by N, then the total resistance of the circuit what will be the total resistance? That will be R by N, that is the total internal resistance of the cells plus the external resistance capital R connected to the circuit, and this will be the total internal resistance of the circuit. And now therefore the current, so the current flowing through the circuit, what is the equation for the current flowing through the circuit? I is equal to E divided by, okay, that is the total EMF is E divided by the total resistance of the circuit, that is R by N plus R. And now in order to get the maximum current flowing through the circuit, so we need to consider the two conditions as I said before. One, if the external resistance capital R is connected much lesser than the total internal resistance, that is R by N, then what happens to the equation for I? The equation for I can return as then. So this term can be neglected then. Why? Because this external resistance is much smaller than the total internal resistance of the combination of the cells. So the equation I can be written as E divided by R by N. And the second condition is, if the external resistance that is connected to the circuit is greater than the total internal resistance of the cells, then what will be the equation for I? I can be written as, so if R is greater, then this term can be neglected. So I is equal to E divided by R. So in which among these two, which condition gives the maximum current? Obviously we know that the first condition, if the external resistance connected is smaller than the total internal resistance, then what happens? And the maximum current will obtain or flowing through the circuit when the external resistance is smaller than the total internal resistance of the cell. Now we are going to learn about the Kirchhoff's law. So Kirchhoff's law is a basic law for the cells. So we have learned the Ohm's law, which is the basic law of the resistance or the electricity, and likewise the Kirchhoff's law is also considered as a basic law which is related to the electric current and the internal resistance of a cells. So, and Kirchhoff's law is mainly explained by two rules. Okay, the first one is Kirchhoff's current law. And what is Kirchhoff's current law? According to this rule, the total current flowing through the junction or a node of a circuit is zero, and that means, and when we describe it very simply, the total current coming in and the total current going out of a junction or a node is always zero. That means the algebraic sum of that current coming in and the current going out of the cell is always, or junction of a cell or junction of a circuit is always zero. And simply we can write as I current exiting plus current entering the circuit is always zero. And see how we can calculate this. See, if there are a node or a junction, a number of circuit which is coming here, see I1, I2, I3, I4, I5. Okay, this is the root path of the electric current. And here see that the current I2 and I4, they are entering the node of the circuit, and I3 and I1, I5, they are going out of the junction. And when we write the sum of this incoming current and outgoing current. So, and always the law says that is always 0. So how we will write this? Okay, the algebraic sum I2, that is incoming, the current entering I2 plus I4. The outgoing current is taken as negative I1 minus I3 minus I5, which is always 0. And here we are not taking this sign conversion. Okay, so I2 plus I4 plus, and the current going out is taken the negative sign. Okay, so I2 plus I4 minus I1 minus I3 minus I5 is equal to 0. And normally the Kirchhoff's current law is basically is a conservation of electric charges. So therefore the total current, the sum of current I is equal to always 0. That is the Kirchhoff's current law says. And second one is Kirchhoff's voltage law. The Kirchhoff's voltage law says that the total voltage of the circuit is always conserved, or it is always 0. Here we consider a closed path loop A, B, C, D. And if we consider here E1, that is the EMF of the first battery cell, and E2 is the EMF of the second battery. And the current I1 is flowing through the resistor, and again the current I2 is flowing here, and from A to C, and the total current flowing from A to C is I1 plus I2, and there is a resistor R3 is connected, and another resistor R1 and R2 is also connected to the circuit, and the total potential drops across these cells is always 0. So in order to find out the total potential drops and the total EMF of the cell, and we need to consider the sign convention. So how we can find out the sign convention and direction of the electric current, and what is the resistance across the cells, and we need to consider the sign convention. So whatever may be, the total potential drop delta V is always 0. That is the Kirchhoff's voltage law says. Then how we can find out the direction of electric current and the direction of resistance in this case, or the voltage in this case, voltage across the resistors. So in order to find out the direction of the electric current and the direction of the voltage, and we need to consider the sign convention. As per the sign convention, so first the EMF of the cell is always taken as positive when we traverse from the positive terminal to the negative terminal. And suppose there is a battery here, and this is the positive terminal of the battery, and if we are moving traverse from the positive terminal to the negative terminal of the battery, then the EMF is always taken as positive. But if we are when we trace the path of electric current, okay, if you are getting the negative terminal first in the circuit, for example there is a battery, and if you are tracing the direction of the electric current, first we are getting the negative terminal for this battery if you are moving from B towards A direction. So then the EMF is always taken as negative. Okay, if you are getting the terminal of the battery first, as we are tracing the direction of the electric current, then the EMF of that battery will be negative, and if we are traversing from positive terminal to the negative terminal of the battery, then the direction of the E will be positive. And second, the resistance. If the resistor is being traversed in the direction of the electric current, okay, so here this is the direction of the electric current, okay, I1, and see when we go here, okay, we get a resistor R1 here, okay, and then if this resistor is being in the direction of the electric current, then the voltage is taken as positive. And if the resistor is being opposite the direction, here see, this is the direction of I1 and the resistor R2 is in the opposite direction. Okay, as we are moving, so as we are moving, as we are moving from A to B, okay, from A to B, and we are getting a resistance, and see, and the resistance is, and what is the direction of electric current? The direction of the electric current is toward this direction. We are moving from A to B. So what will be the potential, direction of potential? The direction of potential will be negative. Why? Because which is opposite to the direction of electric current. Okay. So if the resistor is being in the direction of electric current, then the voltage will be taken as positive. And if the resistor is being in the opposite to the direction of electric current, then the voltage will be taken as negative. That means this I into R, okay, and minus I into R, voltage V is equal to I into R, right? We consider a loop here. So for this loop A, B, C, A, so how we can calculate? So first we consider the EMF of the battery. See, what is the direction of electric current? The direction of the electric current is in this direction, okay, and the positive terminal, okay, we are taking from A to, traversing from A to B, okay, from A to B. As we move from A to B, we will get the positive terminal of the battery first. So therefore the direction of EMF E1, okay, E1 is positive here, right? We are moving from A to B, so we will get the positive terminal of the battery first. Therefore the EMF is taken as positive. And now next we will get a resistance. And what is the resistance? R1. See, the direction of electric current, you see, we are moving towards this direction, A to B. But what is the direction of electric current? B to A. So therefore the potential across this resistance is negative. Okay, then what we get? What is the potential? What is the potential? V is equal to I into R. Then what is the current flowing through the resistance? I1. And what is its resistance? R1 minus I1 into R1. Then next is another resistance. So now we are moving from B to C. There is no resistance. From C to A, again another resistance R2 is connected there. And here R2 is connected. But what is the direction of electric current? The direction of electric current for flowing through this resistance R2 is from A to C. But we are traversing from C to A. So what will be the sign of the potential across the resistor R2? That one will be minus. Then V is equal to I into R. Then what is the electric current flowing through the resistor? That is I1 plus I2, right? So we will write I1 plus I2. And what is the resistance of that cell? R2. And this is how we are finding out the total voltage across EMF and total voltage across a loop by using Kirchhoff's